Welcome to today's episode, where we're diving into the intriguing realm of data storage, focusing on the differences between mutable and immutable storage structures. As we explore these concepts, we'll draw some relatable parallels, especially with the practices of accountants, to underscore the importance of accuracy in managing data. By the end of our conversation, you'll have a clearer picture of how these storage systems function and what they mean for modern, data-heavy applications. Let's start by considering the meticulous work of accountants. Their careful approach to keeping records offers a great analogy for data storage. When they need to make corrections, instead of erasing previous entries, they create new ones. This method ensures that the history of transactions remains intact, providing a complete and accurate account of financial activities. Now, if we think about immutable storage systems, they operate on a similar principle. Instead of modifying existing files, these systems append new records, which helps maintain data integrity. This means that retrieving accurate information often involves reconstructing data from multiple files, much like how accountants preserve historical records. A significant part of our discussion today will center around log-structured merge trees, or LSM trees, which are a prime example of immutable storage structures. These trees are designed to optimize write performance and support concurrent access, making them particularly effective in environments that require high write throughput. Unlike mutable structures that modify data in place, which can lead to fragmentation and decreased performance, LSM trees focus on sequential writes. This approach not only boosts efficiency, but also simplifies the management of data integrity by removing the need for complex locking mechanisms. Now, let's take a closer look at the architecture of LSM trees. At their core, these structures consist of two main components: memory-resident elements and immutable disk-resident segments. The memory-resident components, often called memtables, allow for quick access to data, while the disk-resident segments are designed to efficiently store larger volumes of information. Managing data within LSM trees involves several processes, including flushing and merging. Flushing happens when the memtable reaches a certain size, prompting its contents to be written to disk as an immutable segment. Merging follows, combining these segments to optimize both storage and retrieval. This architecture ensures that LSM trees can maintain high performance while minimizing the overhead typically associated with conventional B trees. Let's talk about the merging process within LSM trees, which is crucial for efficiently combining data from both in-memory and disk-resident structures. By using iterators that read from both sources in sync, we can generate a sorted output without adding unnecessary complexity. During this merging process, we have to consider a few key aspects. For instance, new writes are directed to a fresh memory table, ensuring that both the in-memory and disk-resident trees remain accessible for reading. Additionally, executing merge and cleanup operations atomically is vital for maintaining data integrity, as it guarantees that readers always access a consistent view of the data. As we continue our journey, let's introduce the idea of multi-component LSM trees. These structures consist of multiple disk-resident tables, allowing for the simultaneous flushing of all memtable contents. While this design can boost performance, it also brings its own set of challenges. Over time, the number of tables may increase, complicating the data retrieval process since multiple files might need to be accessed to find specific records. Understanding the distinctions between mutable and immutable storage structures, especially through the lens of LSM trees, has significant implications for modern applications. In a time when efficiently handling large volumes of writes is crucial, the design choices made in storage architecture can greatly influence overall system performance. Immutable structures like LSM trees not only enhance write performance and data integrity, but also simplify concurrency management. As applications evolve and demand more from their data storage solutions, the principles behind these structures will continue to be highly relevant. As we wrap up this exploration of data storage, we've highlighted the critical differences between mutable and immutable structures, with a particular emphasis on log-structured merge trees. By drawing on real-world practices, we've illustrated the importance of accuracy and integrity in data management. Moving forward in this data-driven world, understanding these concepts will empower developers and organizations to make informed decisions about their data storage strategies. Thank you for joining us today, and we hope you've gained valuable insights into the fascinating world of data storage.